Okay, so let me talk you through a problem that deals with conservation of angular momentum, deals with determining angular momentum of a point mass, deals with determining angular momentum of an extended object. So all of the things together we can go through, and it's in variable format, so it's everybody's favorite. So an angular momentum problem. A projectile of mass m sub p is traveling at a constant velocity v naught toward a stationary disk of mass m and radius r that is free to rotate about a pivot through its axis at point O. Before impact, the projectile is traveling along a line displaced a distance b below the axis. The projectile strikes the disk and sticks at point B. Okay, so that's what we have. And the first question asks us, before impact, what is the total angular momentum of the projectile and the disk about the axis? So for this situation, I'm going to be looking at the angular momentum of two things. I'm going to look at the angular momentum of the projectile, and I'm going to look at the angular momentum of the disk. Well, for the projectile, this is a point mass traveling, so its angular momentum is going to be determined by mvr sine theta. Well, it tells me in the problem that m is m sub p. It tells me in the problem that v is v naught, and then we're left with r sine theta. Well, as I'm looking here, the distance from my axis to my point is r. The angle in between my velocity and my r is theta. So I get a triangle that looks like this. And that's theta, where this is r sine theta. Well, in the problem, it tells us that that r sine theta is actually defined by letter b, the distance below the axis. So this becomes b. R sine theta becomes b, which makes sense. The only thing that's going to cause this to torque is this way, not this way. Okay, so then we look at the angular momentum of the disk. Well, the angular momentum of the disk, this is an extended object, so I omega. So then this is going to be a disk, which is 1/2. M it says is the mass of the disk. R it says is the radius of the disk squared, times the angular velocity of the disk before they hit, before the impact, which is 0. So this ends up being 0. So when I come down here and I find the total angular momentum, I'm going to add the momentum of the projectile and the momentum of the disk together, which in this case is just going to be the momentum of the projectile, or mp v naught b. And again, this b is really important. This r sine theta is always going to be that way when you have a projectile traveling into an extended object like that. You can always determine what r sine theta is, and it's not going to change no matter what. This projectile could be all the way out here, and that big distance is my r, and my theta will be smaller, but my r sine theta will still be the same. This is a constant throughout, all the way through. It's constant. Okay. What is the angular speed of the disk and projectile system just after impact? So now they've hit. And my disk and my projectile are one big thing, and they're rotating at some angular velocity v. And it asks me to determine what that angular speed is, v, omega, and it's asking me to determine what that angular speed is after they collide. Well, I know that the initial momentum of the system will equal the final momentum of the system, and I determined the initial momentum of the system in the problem before, so I can determine the final momentum of the system as well. Well, the momentum, this is a big object of radius r of mass m, and I can determine what my angular speed is by looking at the moments of inertia and how those moments of inertia are moving angularly. These two things stick together. So just like how linear momentum, if my objects stick together, I can add their masses and have them go at the same angular speed. When two objects stick together angularly, I can add their moments of inertia and then say that they move at one angular speed. So the moment of inertia of the disk is given by 1/2 mr squared. We found that before. The moment of inertia of the projectile, well, this is just a point mass rotating about some axis. So then its moment of inertia is m, and the distance from the axis to the point mass is r squared. So then my total moment of inertia is those two things added together. Oops, I did this wrong. mp is the mass of the projectile, my apologies, times r squared. So then my total moment of inertia is that. And when I find my final angular momentum, it's that moment of inertia, 1/2 mr squared plus mpr squared times angular speed. Now, if I'm trying to figure out what that angular speed is, I'm going to use conservation of angular momentum. So I'm going to say my momentum at the beginning, mp v naught b, equals my momentum at the end, 1/2 mr squared plus mpr squared times omega, and determine omega equals mp v naught b over 1/2 mr squared plus mpr squared. And I could simplify that somehow. I can multiply everything by 2 and get this to be 2 and that to be 2 and go from there, but I'm not going to. I'm just going to leave it like that and move forward. So again, we use conservation of angular momentum to solve those pieces in order to get to this question, which deals with energy. What is the kinetic energy of the disk and projectile system after impact? Well, after impact, the only type of kinetic energy I have is rotational kinetic energy. And I know I can determine rotational kinetic energy by taking 1/2 I omega squared. Well, luckily for me, I determined both of those in the problem right before this. So I'm going to plug them in. 1/2 I, 1/2 mr squared plus mpr squared, omega, mp v naught b over 1/2 mr squared plus mpr squared squared. Whew. Okay, so we got this special thing going on here, but a lot of stuff actually cancels out of this. For example, this denominator is going to be squared, but one of them will cancel with the numerator, with this piece right here, this I value. So then what I get is this, 1/2 times mp squared v naught squared b squared over 1/2 mr squared plus mpr squared. Or, to simplify, mp squared v naught squared b squared over mr squared plus 2 mpr squared. And that's my kinetic energy. And it's all rotational. So then in this last question, it asks me how much is lost. Well, what I have at the beginning is I have some translational kinetic energy, and then at the end, that goes to a rotational kinetic energy, and some energy is lost in this collision because it's not a perfectly elastic collision. So then what I need to figure out is how much of that is lost. Well, I know at the beginning I have 1/2 mv squared, and I know that that's it because that's the only object that's moving, is this projectile, and it's moving with some kinetic energy. And then at the end, I have mp squared v naught squared b squared over mr squared plus 2 mpr squared. So if I want to figure out how much is lost, I find the difference in those two. And that's my answer. Okay, so again, we used angular momentum. We started with, okay, what's my angular momentum of my projectile? What's my angular momentum of my disk? And how do I put those together? We used that then to find the angular speed at the end, using conservation of angular momentum. We used our speed to find our kinetic energy, and then we were able to figure out how much kinetic energy was lost from my system. Go ahead and take a look at this video again, and if you have questions, please let me know.